Okay, so just keep going for our class. So actually, we have two approach to describe the motion of the fluid particle. So the first one is we call that is Lagrangian approach. The second one is Eulerian approach. So as you see the following equation showing here, the Lagrangian is very easy because just pick up one fluid particle and then you track the fluid particle. So the idea is we need to know the initial point of the fluid particle. So we have the t0 times, and we have the x, y, z positions. And then because we have the velocity field, and then we pick up one times like the t1, and then we can follow the initial point, and we have the velocity functions. So that's why we can predict the positions for the t1. Okay, so Lagrangian is very easy. The idea is quite simple because we just need the initial point of the fluid particle, and the second we need the velocity field, and then we can predict the position for the fluid particle any times. So let the typhoon, currently the typhoon may be located on oceans, but we know the field, the velocity field of the typhoon, so we can predict how many times the typhoon can attract the Taiwans. Okay, so that's the similar ideas for the Lagrangian approach. So how different for the Euler? So the Eulerian is different is we only need to know the spatial functions. We describe the spatial location as function of the time. Okay, so it's better idea to understand two approaches. So here I just show out one example. This example is quite simple because we just drop the one particle, and as you can see, this is the questions for the falling under the action of the gravities. So the idea is, if we follow Euler approach, if you would like to describe the motions for different timings, okay, so the idea is you can try to balance the energies, because we know this is the questions we can solve by energy balance. What I say, because usually you know in here maybe the initial velocity is 0, and at this time is t0, and maybe several seconds later we have a t and the t final, and what is the velocity? What is the velocity in here? So the idea is we can just make the energy balance based on the potential energy and the kinematic energy. So for the kinematic energy, we know exactly is 2/1 mv squared, right? And it's equal to mg z. Z is the elevations. So we exactly know what is the v. What is the v? So you just cancel out the mass and then move the two to right hand side. So you know it's 2gz. And because here is square, so you take a root. So you have a root and a 2gz. Okay? So the idea is we don't need to know where is the initial positions. And second, we don't need to know the velocity field first, because we just have the energy balance, and then we know anywhere z, and we can compute the velocity relatively to this point. So that's the advantage for the Euler, because we don't need to know the first initial point. Where is the initial point? The second, even though we don't know the velocity field first, but then we can base on basic principles and try to find out the velocity field as function of the spatial locations. Okay, so you just can see the directly link the spatial location with the velocity. But for the Lagrange, it's different because we need to know the initial time, and then we can predict where is the location. And then we need to know the initial time, or what time it is, and then we can predict the velocity for that time point. So the difference is Eulerian look like the velocity field as function of the positions, but the Lagrange, we need to have the velocity functions, and then we need to have the t functions, and then we can predict the particle motion and the velocity field of the particle. Okay, so and if you have some confusing, so the table just summarize and make a comparison between two approaches. So this is for the Lagrange, and this is Eulerian. And then you just take a look what I highlight with the red line here. So usually Eulerian approach just focus on the spatial location and some motions as function of the spatial locations. And you see what is the independent variables. First one is for the Lagrange, we need to the initial positions and the time. If we don't have, we cannot predict the location for the next time step. But for the Eulerian, we just have the spatial locations, and then we can predict any locations for the like the velocity field. Okay, so the difference, like the mathematics for the Lagrange, always is the initial conditions. If we have the initial condition, and then we can predict any times of the physical property for any times. But for the Eulerians, like the boundary conditions, if we have the boundary condition for spatial, and then we can predict anywhere's location for the physical properties. Okay, so for the fluid mechanism, usually we use the Eulerian. Because Lagrange, like the baseline, we need to check the fluid particle at different time. But in real case, it is very difficult. We cannot capture the fluid particle in the liquid easy. But for the Eulerian, we only need to have the functions, the physical function as function of the spatial, so we can predict any physical properties at any locations. So that if we discuss with the velocity field, usually we use the Eulerian methods. We don't use the Lagrange. Okay. So the second, as I mentioned previous class, we have the unsteady flow or steady flow, and we have the certain definitions of the steady flow. That means if the steady flow, the meaning is the physical property didn't change with the time increase. So again, if we call that is the uniform flow, that means the velocity fields didn't change with the spatial change. Okay, so if in that case the the differential v with the spatial is equal to 0. If non-zero, that means we call that is the non-union flow. Okay, so you see if the union flow like the linear and the parallel for each string lines. Okay, but if you is non-uniform flow, so we have the convergent flow like this, and then you can see the string line even though not the parallel and will cross over at the certain locations. And another flow we call that is vortex flow, like the rotational flow. And we will provide the definitions for what we call that rotation flow. Okay, so so in here the most important is if the velocity didn't change with the spatial. That means the gradient is 0. So we call that is uniform flow. But in real case, it is very difficult to have the uniform flow. Okay, so usually our flow is non-union flow. So, and the two important flows. The first one is a laminar flow and the turbulent flow. And there are some physical definition, but we don't tell you too much in here. And the most important is if we look the velocity profile, you see this is a laminar flow, and this profile, velocity profile, we have seen before. When we discuss the like the shear stress is equal to the mu is our viscosity, and if there are some velocity gradients like here shown, and then we call this is shear stress contributed from the viscosity properties, and this is dynamic viscosity, and we have the velocity gradients. So in here, maybe the x is along these directions, and this is the y. So we know that the velocity profile will change with the along the y directions. So that's why we can discuss with some shear stress contributed from the viscosity properties. Okay, so this is a laminar flow, and the right-hand side is the turbulent flow. As you see, this is the velocity profile for the turbulent flow. So the idea is for the turbulent would like to change the velocity profile to be the uniform flow. So actually you can see the shape is similar to the uniform flow. What I say the uniform flow is the string line, the amplitude of the velocity is the same, and each string line is parallel each others. So we call that a uniform flow. If for the uniform flow at the certain profile, the velocity will be the same values. Okay, but you see there are some fluctuations. Okay, this fluctuation we call that is AD, the AD flow. So for the turbulent flow, the physical meaning is some physical properties would like to change the velocity profile to be the uniform flow, but it's not the true uniform. So there are some fluctuation velocities, and we call that is AD. So until now, there is no any mathematic representation equations to describe the turbulent flow, because there are some fluctuation is randomly. So we cannot predict accurately for the fluctuation velocities. So in that case, usually we will find out the average velocity for the uniform flow, and we can plus some fluctuation velocity like the prong here. But as I mentioned, there is no any solutions for prediction the U prong. So until now, it's very difficult to understand. So for the turbulent flow, usually we have the laboratory experiment to understand what the turbulent flow behaviors. But certainly, currently, we don't have any mathematical representation equation to describe the turbulent flow. Okay, so for this, it's very important. Some scientists, they provide the Reynolds numbers. So this is very important. What is the Reynolds numbers? The Reynolds numbers just provide some criteria to distinguish which one is laminar flow over the turbulent flow. As you see here, I show up the certain values. If the Reynolds numbers less than 2,100, and you can call that is laminar flow. But if the value is higher than 4,000, and then you call that is the turbulent flow. Okay, so this is very important dimensional list, the parameters, the Reynolds numbers. As you see, I provided the formula for the Reynolds numbers. The first one is, you can see the ratio rho ud divided mu. And the mu is the viscosity. So you understand if the viscosity mu larger, so the Reynolds number is decreased. Okay, so that's why the high viscosity will have the low Reynolds number. So usually the flow is laminar flow. But if your viscosity is quite lower, so the liquid particle will randomly motions and active. So the motion will move to the turbulent flow. Okay, and what is the rho? Rho is the liquid densities. And what is U? U is the velocity. And the D is diameter of the pipe. So this formula only for the pipe flow. This formula only for the pipe flow conditions. So if we have some flow in the pipe, and we can define the flow conditions in the pipe, we can identify the flow is laminar flow over turbulent flow based on the Reynolds number shown here. Okay, so the idea is for the turbulent flow usually is unsteady, but the laminar flow may be sometimes steady, sometimes unsteady. So that's why we introduced the steady and the unsteady flow before. And you see, the laminar flow usually the velocity profile is parabatic. And then here I show the ratios. You see the ratios of the mean velocity to center line velocity usually is 0.5. The mean velocity is U bar, right? And what is the center line velocity? For the laminar flow, the center line velocity, this is a velocity profile. So the center line is in centers. So the center line velocity is here. Usually is U maxima, because the center always has the highest velocities. Okay, so that means for the laminar flow, the U bar and the divided U maxima, the ratio is equal to 0.5. This is for the laminar flow. But you see for the turbulent flow, here, the U bar and divided the U center line, the ratio usually is around the 0.8 to 0.9, because for the turbulent flow, the velocity profile like this shape. So the center line is quite close to the U bar velocity. So the ratio is quite close to 1. So it's this is a very obvious difference between the laminar flow and the turbulent flow for the velocity ratios. Okay, so you need to keep it in mind, and in our following class, I will tell you why this ratio like this, like I showing here. Okay, so but another important you need to keep in mind for the Reynolds numbers formula in here, and this is dimension these parameters. Okay, so the final two flow, the first one is viscosity flow and the inviscid flow. Okay, so the difference only here is if the force associated with the viscosity shear stress are larger enough, that means you cannot ignore the shear stress for your problems. So in that case, we will call that is a viscous flow. So if the force do not affect the dynamic motion of the particle, and you can call that is inviscid flow. Okay, so in our class, usually we consider inviscid flow because for our problems, usually our target is water. So water, usually the viscosity value is quite lower, so we don't consider the shear stress contributed from the viscosity. Okay, so this is our final flow. So summarize, the first one we teach you the steady and unsteady, and the second one is uniform and non-uniform, and the third one is laminar flow and turbulent flow, and the final is viscosity or inviscid flow. Okay, so this is a total our flow properties we will discuss in the following class. Okay, so we still have 10 minutes, so I just go quickly for these slides. So usually we, as I mentioned, if we consider inviscid flow and we have relatively higher Reynolds numbers, that means our flow condition is inviscid flow and looks like the turbulent flow because we have the higher Reynolds numbers. Okay, and then you see the blue line is the string function, string lines. If the string line is quite close to the particle, and you will see the string line will attach along the particle shape. And usually we call that this is attached flow or boundary layer flow. And then after this point, you can see we indicate this point is flow separations. And after the flow separation, there are some wake flow. So what I emphasize here, the wake flow is very, very, very terrible flow. So, and the motion behavior like the turbulent flow. So for the fluid problem, we don't like the turbulent flow because the turbulent flow have some destroy powers for the infrastructures. So we are afraid the wake flow in here. So I just show one example here. And before I show the movie like here shows, I would like to tell you for the wake flow there are some eddies, or we call that is vortex shadings. The vortex shading will induce some oscillatory force. The oscillatory force, that means some force with harmonic period. If the harmonic period is consistent with the natural frequency of the structures, they will dance together, right? Like the building. In Taiwan, the building height, maybe the building is 10 floor buildings. And then you minus 10, you divide it 10. and you have equal 1, right? So 10 floor buildings divided 10 is equal to 1. And the 1 is the nature period of the building, 1 second. So if your building is 100 floors buildings, and you divided 10 is equal to 10, and the unit is 10 seconds, and the 10 seconds is your building period for the vibration. So if there are some earthquake coming, and the earthquake wave is the period of the earthquake wave is equal to 10 seconds. And then if your building is 100 floors buildings, and it will shake a lot. Okay, so the idea is for that. This is the bridge. As you see, the installation in 1940s, and finish the installation in July, and it will be broken on November. Only alive 5 months and broke. This is a suspending bridge, and there are some the wind speed is high enough, so there are some turbulent flow, and the turbulent flow induce some oscillatory force, and the oscillatory force period is consistent with the bridge natural frequencies. And then you see the bridge just dance with the wind speed higher enough, and the bridge start to dancing. Okay? But in that time, you see the people don't care, just work very slowly because it's quite like the slow motions. The period around the 10 to 100 second period, so quite slowly. So this is a very good example to tell the people if you design the bridge, and there are some problems you need to deeply consider it. If not, this is just you see it's open in July, and in November it's broken. Okay, so it's very terrible. And you see, so finally just broke. Okay, and then you can Google that, and this bridge already reinstallations, and currently it's not the suspending bridge, and they redesign the structures of the bridge. Okay, so this is I just show you. Sometimes we don't care, and we finish some structures. But if we don't care, there are some very terrible things will happen in the futures. Okay, so we start here. OK， 然后今天我们因为是新的开始，对啊，让大家新的开始，所以我们重新发新的考卷，所以大家自己来，是不是来拿好了比较快？
上次没看到成绩，所以
我们再请，因为我们会把你没拿到的话，有2个方法，一个是去找助教，要不然你就是寄信跟助教说你想要拿回那个考卷，对。好，那酷了。 我们跟大家说的很清楚，因为是一个重新的开始，所以之前的那个我们说重新开始，上一节课我们说过嘛，之前的就是前30%，然后这一份考卷开始以后，从第4章到第几章，4、5、6，会是接下来的30% 的比重，所以我们会用这一份开始重新再算你的30% 的成绩，所以好的开始就是成功的一半。大家看一下题目，我们希望再帮大家把一些分数再追回来。好，第一题，这次跟之前有点不一样的是，分数的比重不一样，对吧？前面这一题是第一题，我们只有20%，就只有3个选项 A、B、C、D。请问你现在这个速度函数，它是怎么样的一个速度场？它是一个怎么样的速度场？那我把这个再放大一点，重点是看一下它的有哪些 component， 然后去回答一下。我可能把电灯光暗一点。那我们有给分的方式，这个再特别强调一下。如果因为有2个，左边跟右边有2个答案，如果你写错一个，那你还是会拿到10分。所以不是你 A、B、C、D 选错了，我们就不给你分数。你懂我意思吗？你就是不要去选那个全部都是错的。好，我已经讲得很明白了。好，所以我们不会因为你写错的答案，我们就不给你这一题分数。我们会将就，比如说你哪里写对了，我们会给你一半的分数。好，第二题，我应该也不用强调，这个我们在课堂上练习的时候也有这一题。第二题就是要求流场，求它的流线的函数长得怎么样子。所以你只要最后有写出方程式的样子，那个就是它的流线方程式。那助教就会看你写的对不对。OK， 所以第二题有没有问题的？好，那没有问题，我们就赶快来写。